So electrons can behave like waves. And this was proposed by Louis de Broglie. He only died in 1987, which really isn't that long ago. Back in 1924, he proposed that particles can have wave-like behavior. So we see the wave nature of an electron most clearly when we look at electron diffraction. We talked about how waves of light, waves on the water, undergo diffraction when they go through a slit, right? We looked at that double slit experiment, the guy on the beach with the box. Electrons are particles, but they also behave like waves. And we saw that light is a wave, but also behaves as a particle at times. What's really trippy about electrons is the interference pattern that we see is not caused by pairs of electrons interfering with each other, but single electrons interfering with themselves. And that's only possible because the electron is also a wave. So 1927 got some proof that electrons produce interference patterns. So here we've got a source of electrons. So we're shooting electrons at this barrier, much like the waves coming at the slit. And so we've got two slits here. And what we observe over here is an interference pattern, much like is seen with visible light. This demonstrates that electrons are behaving as waves. If they behaved only as particles, we would expect what some people expected when they looked at that double slit experiment, that there would just be two bright spots or bright lines. Because if they're behaving as particles, as the particle comes, if it hits the wall, it just bounces off. If it hits the slit, it goes straight through. It's not affected by the slit, right? You think about taking an airsoft gun or something and shooting it through a crack in the door, right? As the airsoft pellets go through that small opening, they're not touching anything. The opening doesn't affect them at all. And so that's how particles behave. This is not what happens with an electron. So the wave nature of the electron is an intrinsic inherent property of electrons. De Broglie predicted the wavelength of a particle was inversely proportional to its velocity. So that gives us what's known as the de Broglie relation, where lambda, the wavelength, is equal to a constant, h, divided by the mass times the velocity of the electron. H is known as Planck's constant. It's 6.626 times 10 to the minus 34 joules times seconds. So if we know the wavelength, and the mass, we can predict the velocity. Or if we knew the velocity and the mass, we can predict the wavelength, etc. What is the velocity of an electron that has a de Broglie wavelength approximately the length of a chemical bond, which would be about 1.2 times 10 to the minus 10 meters. So de Broglie wavelength, we need the de Broglie relation, which, brain fart, just forgot it, there it is. Okay, so lambda equals Planck's constant divided by the mass of the particle times the velocity of the particle. We are asked to find the velocity. So we need to rearrange this equation and solve for v. Cross multiply to get rid of the fractions. So that gives you mv lambda is equal to h. Then divide by the things you want to get rid of. And we've got velocity is equal to Planck's constant divided by the mass times the wavelength. Planck's constant is 6.626 times 10 to the minus 34. I do not expect you to remember that. I'll give that to you on an exam. And the unit is joule seconds. We're dividing by the mass. They didn't give us the mass. Hey Siri, what's the mass of an electron?
The electron is a subatomic particle, symbol E or Greek letter beta, whose electric charge is -1 elementary charge. Shall I continue?
Yes.
Electrons belong to the first generation of the lepton particle family, and are generally thought to be elementary particles, because they have no known components or substructure. The electron has a mass that is approximately 1.1836, that of the proton.
Well, that was singularly unhelpful, Siri. Well, Siri wasn't helpful. I had to look it up myself. The mass of an electron, 9.109 times 10 to the minus 31 kilograms. So let's put that in here. 9.109 times 10 to the minus 31 kilograms. And we're given the wavelength. So 1.2 times 10 to the minus 10 meters. Now, what do I always tell you to do before you get out your calculator? Look at the units. Those units look like a mess, don't they? Looks like nothing's going to cancel out. So a joule is equal to a Newton meter, which is equal to a kilogram meter squared per second. So up here I have joules times seconds, kilogram meter squared per second squared. There we go. Up here I have joules times seconds. So if I take a joule and multiply by a joule second then would be a kilogram meter squared per second, right? So that's the unit on top, and I'm dividing by kilograms and I'm dividing by meters, so what do I have left? Meters per second. So 6.626 times 10 to the minus 34 divided by 9.109 times 10 to the minus 31 divided by 1.2 times 10 to the minus 10 gives me a really big number. 6.061 times 10 to the 6 meters per second. 2 sig figs would be 6.1 times 10 to the 6th meters per second. Yes?
So when she converted the joules from seconds to the kilograms meters squared, do you just change, on the problem, do you just change the units and leave the numbers alone? Or?
Yeah, you would just change the units, you would leave the numbers alone, because the joule is actually a combination of these other base units of the metric system. So what you can do here is you can take, so we had joule seconds, you can substitute in what a joule is, a kilogram meter squared per second squared, and that was times a second. So then we see the second cancels one of those, this meter cancels one of those, and the kilograms cancel. This problem was set up with the correct units. So if this whole joules to kilogram meters squared per second thing is confusing, don't worry about that too much. Any other questions? So when we were talking about Schrodinger's cat, we were talking about how the absolutely small can exist in all of its possible states at the same time, but that when it is observed, those different realities collapse and it has to be one or the other. So if we design an experiment so that we can observe, try to observe both, or actually just observe the electron at all. So here, if we take this double slit experiment where we were seeing a diffraction pattern and we shine a laser beam, I know that looks like a, what does that look like? It looks like a lightsaber, doesn't it? It's a laser beam. If we shine a laser beam here, the laser beam allows us to see which slit the electron's going through, and so the electron starts to behave as a particle. So you turn on the laser beam so that you can identify which slit, and then you get the bright spots. It's behaving like a particle. You turn off the laser, you get an interference pattern. It's behaving like a wave. Which one is it? It's both. Does that bother you? Should bother you. It's disturbing. So uncertain, right? Heisenberg's uncertainty principle can be mathematically stated this way. Delta x, that would be the uncertainty in the position of the object, the electron, times the mass of the electron times its velocity. So delta v is the uncertainty in the velocity, must be greater than Planck's constant divided by 4 pi. So the bottom line here is we cannot simultaneously measure the position and the velocity of an electron. The more we know about one, the less we know about the other. And so there is inherent uncertainty. You can't know both at the same time. Any questions? So classical physics says that particles move in a path that's determined by their velocity, their position, and any forces acting on them. So a baseball. A baseball obeys the laws of classical physics. This is called determinacy, where the present determines the future. With an electron, we can't know both the position and the velocity. We cannot predict the path that it will follow. This is indeterminacy. We cannot predict what it's going to do in the future based on its position, its velocity, and the forces acting on it. We can only describe the future statistically. We can say, well, it's probably going to do this, but we can't say for certain. With a large object, we can say for certain that it's going to do this. This force is acting on it, it's going to cause a deflection, etc. So the best we can do describing what electrons are going to do is describing the probability. So classic trajectory, you've got a baseball player hitting a ball, and there are forces, the force of the bat, it goes in a direction, it's maybe got some spin on it, you've got wind blowing on it, you've got gravity pulling on it. You can measure those different forces, and you can calculate where the ball's going to go. I watched a high school baseball game last night, and it's even more apparent with the professional baseball players. Through practice, they have trained their brains so that they can watch that baseball and they can predict where it's going to go, and they can run and get under the ball and catch the ball. That's your brain doing a lot of calculations that you're not even aware of. But we've learned that we can predict where it's going. So that works for baseball. Doesn't work with electrons. So if a pitcher pitches a baseball, he can predict where it's going to go. And he can pitch it in the same place every time by doing the same thing with his body, right? You can't do that with electrons. You can make a pitching machine for baseballs, right? And it shoots the baseballs out in the same way every time. If you made a pitching machine with electrons and sent them at the same velocity in the same direction every time, they would not go in the same place. They would go in different places because they are not predictable. The best we can do is to make sort of a target here and say, well, there's a 20% probability that the electrons will be in this smallest circle, 40% in this larger circle, 70% in this circle, but there's a 30% chance that the electron's going to be out here. It might hit that lady between the eyes. You can't predict where it's going to go. So we could make a graph of the number of particles hitting within a distance from the center of the strike zone. And so we do have the highest number hitting right in the center. And as you go away from the middle of that strike zone, the number of particles is going to decrease, but it's never really going to go to zero.